Okay, well, I'm happy to say the fire's out in Santa Barbara. It did get worse for many of you who were there. It got worse after you left. It got better, and then it got worse, then it got better. So I don't have any images of it, but you can imagine 100-foot flames are pretty exciting. Okay, so what I want to talk about this morning is adding material to white dwarfs, in particular thermonuclear instabilities. But I want to start by just reminding you a little bit, and maybe Sturl's done this, about just typical white dwarf masses. So this is what's known about what we call the white dwarf initial final mass relation. So on the x-axis is the initial mass of the star. These are from data from open clusters. Excellent. Okay. And this is just to remind you that the most massive white dwarfs are only coming from the most massive stars. And of course, because of the initial mass function, that means when you look at the white dwarf mass distribution, most of them are piled up around 0.5. And massive white dwarfs are actually rather rare. So white dwarfs in the field in isolation with masses above 0.8 are quite rare. And things above 1.3, which I'm going to highlight towards the end of my talk, are even rarer. And when they're found, they're often speculated to be from white dwarf mergers. And so the reason I want to do this is that what I'm going to show you today about white dwarfs that we see via thermonuclear flashes, there's a lot of evidence and data that tends to say that the majority of those are actually from white dwarfs of masses 0.8, 0.91. And the reason for that, as hopefully you'll begin to understand as I go through my lecture, is that the higher gravity on those objects allows for shorter recurrence period, therefore more frequent outbursts. And that's probably why we have this preference in terms of classical novae for seeing objects that are more massive. That's at least how we understand it, but it is important to highlight that it is going to be different than what you see in the field. Okay, so the task I was given by Sturl was to talk about objects that undergo thermonuclear fusion due to piling on of material from a binary. And Sturl's done a great job at summarizing some of the binaries that make these systems, and I will also highlight that. But typically, an isolated white dwarf is done with burning. It's made of carbon and oxygen. It has a helium layer and a little bit of hydrogen left. And the rest of those envelopes are lost in strong winds, and that's indeed this plot that apparently Sturl showed. This dashed line is more or less the white dwarf mass at the first helium shell pulse on the AGB. And most stars, after that point, have winds that lead to the ejection of all the material. But if you're in a tight binary and you can add material, you have an opportunity to actually undergo fusion again, in this case, via the material that's sitting on the surface. And so, as I'm going to highlight, these are actually pretty rare systems, but the fact that the outbursts are frequent and actually quite bright allows us to really study them in distant galaxies. And indeed, these are the most frequent transients that you would see in a typical galaxy. So let me give you two more numbers, then I'm going to go to the blackboard and start doing some algebra for you. So first off, typically about 1% or less of white dwarfs are in binaries that can undergo an accretion of material. And one number to keep in mind first is the amount of gravitational energy release you get when you put material onto the surface of a white dwarf, which is just the gravitational binding energy. And I like to put that into nuclear units, which is a few hundred kilovolts per nucleon. And fusion of material, of course, is much more. We can get 5 MeV per nucleon if you have cosmic mixture of hydrogen and helium going to pure helium. Hydrogen to helium is 7 MeV, but you already have some helium in a cosmic mixture. So it's about 5 MeV per nucleon when you go from cosmic mixed solar mixture to helium. And when you do helium to carbon, it's less. It's around a 1 or 2 MeV, 1 MeV per nucleon. And so if the object was stably burning, the accretion, most of the light would be coming out, and most of the energy would be coming out from fusion. But what we're going to see is that it's really rare for any of these systems to undergo steady fusion. Rather, they build up large piles on the surface and undergo flashes. And that's what we see as classical novae. Okay, so at some point I want to give you numbers, so this is a good point to do that. If I look in a distant galaxy, take something like Virgo, or M87 in Virgo, if I have 10 to the 11 solar masses of old material, I'm typically making about 2 new white dwarfs per year. if I'm looking at that same galaxy, I will see about 20 classical Novae explosions per year, what I'm going to describe, which we know are fueled by hydrogen. And that actually, from that, we can infer a birth rate of the cataclysmic variables that make them of about 1 every 400 years. Now, Dan's going to talk about type 1a supernovae later today. That's typically in a galaxy like this about 1 every 250 years. So if you want to start to understand some of the rarity of things, roughly 1 in 500 white dwarfs explode as type 1a supernovae. We're pretty confident that a type 1a is the complete disruption of a white dwarf. And that's true for about 1 out of 500. But keep in mind this rate of the classical novae is extremely high. So there are about 20 per year relative to 1 per 250 years. And so the classical novae are the things we see the most frequently in a distant galaxy in terms of a large outburst. Tomorrow, probably tomorrow, I'm going to talk about systems that are undergoing helium accretion. They have events that are less frequent. Indeed, we have very few prototypes. They're so rare that maybe it is down to 1 every 200 years or so, which is sort of almost the same as the rate that we see type 1a supernovae, probably coincidentally, we think. So before I go to the blackboard, let me stop and see if there's any questions so far on just setting the stage for you.
Why do you
Yep.
say about white dwarf
Yep.
measures separated to 1A?
Why am I talking about white dwarfs separately from 1As? Well, we think
They still,
we
so isn't it the 1A here region?
well we think the type 1a supernovae are the thermonuclear explosion of a white dwarf.
Okay. Via accretion.
Yeah, that triggered by some event, a merger or accretion. But I would say I'm looking at Dan. He can correct me if he's going to say something different. I think we can say with confidence it's a solar mass of material that's undergone rapid fusion, making half a solar mass of nickel. That's most likely a white dwarf. Yeah.
So say that 1A are more frequent than the birth rate of the CV?
Well, they're.
250 years.
I'm not going to argue that 400 and 250 are different for today's purposes. Yeah, don't believe that there's any inequality
So
here.
it's either every CV is giving you 1A eventually, or
Yeah, I don't think there's any. I personally think there's no connection between CVs and 1As. Yeah. So some of these are just. Fair question. Don't make something of those two numbers being comparable. I wouldn't. You're free to, but it's hazardous. Okay. Yes. I think that's Dan's problem. The question was, what about the white dwarf merger rate being comparable to the 1A rate? I think that has some meaning, yes. But I'll let Dan. I'm setting him up. Okay. Any other questions? All right, so things I'm going to have to explain, some of which I will and some of which I won't. I'm going to definitely go to the blackboard and explain why the burning is thermally unstable. I'll then revert back to PowerPoint and walk through how a thermally unstable model evolves. I'll talk about the rates of the event from a given system. How do we understand their outcomes? I will claim there's still lots to do, not so well. And then I'll end with, do we have any good predictions that we can test? And I'm going to emphasize super soft sources because that's something where we actually have a theoretical understanding. By we, I mean the community, that is testable. So, okay, so I'm going to break to the blackboard now. I'll look back. See if I can get his attention. Okay. He's there. I can see him. Oh, I can just unplug. Oh, there it goes. He's doing something. Okay. Looks like the blackboard's been used. Good. Okay, so what I want to talk about is as I add material onto a white dwarf, what we're going to first calculate is what if it could burn the fuel at exactly the rate it's accreting. So we're going to have a typical accretion rate. What I'm going to call m dot is the accretion rate onto the white dwarf. And I'm going to give numbers later of the typical values of this. Sturl also highlighted that. That really is a binary evolution question. And there's a typical energy release as material burns. And as I said before, it's 5 by 10 to the 18 ergs per gram when you burn cosmic to helium. This is 10 to the 18 is about an MeV per baryon. And when you're doing helium, this is then less. It's about 1 by 10 to the 18 ergs per gram. Helium to carbon. Okay? So if I'm in steady state, the luminosity of the object would just be Q times m dot. It's very simple. Because these numbers are much bigger than the gravitational energy release from getting onto the surface. Okay? So how do we understand what this may look like within the star? So let me first draw a schematic. So to the right is into the star. I'm going to be a little bit vague on what the coordinate is, but to the right is going in. Okay? And I can plot the luminosity at a given coordinate. And it should look something like this. This would be Q times m dot. This region is where the burning is occurring. And in this region, I'm going to just call the advection zone. Okay? So the material is come onto the white dwarf. It's gravitationally bound. There's been something at the surface, either via a disk or a boundary layer, that's allowed for the gravitational energy to escape. And now we're really just doing a star. Okay, we're just doing an unusual star. We're doing a star that's actively accreting and adding mass to its surface. Okay? Surface is here on this side, because this is in, so this is out. Yep. And beneath the burning layer, there could be heat going in, there could be heat going out. That's why I'm sort of not so clear what's going on here right now. Okay. All right? This is the whole star going in. Yeah. So that I just keep going down to high densities to the core. The core is to the right. That's correct. That's right. Yeah, core is to the right. So I'm not. Well, to me, it's all a star. So I'm not differentiating. This is the envelope of hydrogen and helium. So thank you. So this would be the hydrogen helium. This would be, if I'm in stable burning, this would be helium. Right? And this is where it's all burning. Yeah, thank you. Okay? And then down here is carbon oxygen somewhere. Say. Okay, or oxygen neon. Okay, so that's all I got to do. I have to figure out where this burning happens so I can understand the properties of the burning. And this we can do rather simply. So as I go into the star, the temperature will rise because the heat has to get out. And so that's just heat transfer via radiative diffusion. So in that advection zone, the luminosity at any coordinate r is just minus 4 pi r squared times the flux. Okay, and the flux is just 1/3 c over kappa rho ddr of a t to the fourth. Right, so it's just radiative diffusion is all that's happening. And again, the luminosity is constant, roughly at this value qm dot. And so I can actually just understand how the temperature has to rise to go in just to get the heat out. Okay?
How we show it's stable to convection?
Yeah, it is stable to convection. Yeah, I won't show you, but it is for this solution. Yeah, yeah, fair question. We'll be able to show it after we get to a certain level. It would be a good homework problem during coffee break. Okay, and the atmosphere is in hydrostatic balance, or the atmosphere envelope is in HB, hydrostatic balance. So that means that dPdr is just minus rho g m of r all over r squared. Okay, so this is the density of the material. M of r is the mass enclosed, and r is my coordinate. Okay, so this is all I have to solve are these two equations. Many of you have done this probably. How many of you have done stars? Raise your hand high. Everybody. Okay, I don't have to even do this then. Okay. Everybody knows where I'm going? Oh, you don't remember? Okay. Okay, that's only to be heard by your instructor, not by me. Okay. Okay, so there's a way to combine these two equations. Some of you may remember that. But I'm going to make a few simplifying approximations because basically I want to keep moving fast. So I'm going to assume something that's really risky, which is that the layer is thin. What I mean by that is I'm going to assume that this layer in delta R is much less than the radius of the star. Okay? And I'm also going to assume that the mass in this layer, delta M, is much, much less than the mass of the star. Those are two assumptions I'm going to make. This one is really a good assumption. This one's a little risky. Okay? But this is a great assumption, as you'll see when I show you the answers. Okay, well that allows me to simplify some things. I can define a gravity, which is then just gm over r squared, right? Things are simple because there's only one radius in the problem. And I'll also have a constant pressure assumption in a minute. So let's see. I'm trying to get the board. Okay, that gives me enough room. Okay, so I can just take the ratio of these two equations. Notice this is a 1/3 AT to the fourth is the radiation pressure. So then I just get that dP rad dP. So if I take the ratio of this equation to this equation, is then very simply kappa L over 4 pi GMC, or just L over L Eddington. Pardon me. And the Eddington is 4 pi GMC all over kappa, and I'm also assuming kappa is constant for now. And I'm going to assume it's just electron scattering. Again, not bad for this case. Not bad for this case. Okay. So this you've done before, probably. This is called the Eddington Standard Model. How many people have done that? Less than did stellar structure. Okay, we're discovering how far you got in the book. Okay. So the key thing that we're going to see that's coming up is this Eddington limit, which I think has probably been described before my arrival. But it's really going to play a key role in what sets the stable burning regimes for these white dwarfs. Okay? Okay. So we're almost there. Let me first then use, let's see, I guess if I can do this. Okay, great. I don't lose my formula. Got it. So let's give some numbers first. So for this Eddington, what would the m dots be? So right, so first let's get an accretion rate given that energy release that would give me a luminosity. That's the Eddington number. Okay, so if I'm doing hydrogen helium to helium, right, that sets the Q value, and it also depends on the opacity. For that, I get 4.3 by 10 to the minus 7 solar masses per year for a 1 solar mass object. M dot Eddington, when I'm doing helium burning to carbon, which I'm going to do tomorrow, is therefore going to be higher because the Q is less, right? And it's about a factor of 10 down. So really about a factor of 8. So it's about 5 by 10 to the minus 6 solar mass per year. Okay, so that just is setting the scale, right? So this is the scale at which, again, a stably burning object would be creating a luminosity of the Eddington luminosity. And of course, this physics doesn't know about binary evolution. So we're going to find out when we do binary evolution where we land in accretion rate space. And we're typically going to land below this value, but not always. Okay. Okay, so it looks like I actually haven't done anything yet. I'm just writing down equations. But what's a little bit shocking is how far you can get. And so what I want to do now is start to calculate where this burning actually happens. Okay? So I guess I want to, I think I can erase this. So does anybody want to integrate this equation for me? What's the right-hand side? Is it changing as I go into the star? Huh? If I'm in the advection zone, if I'm in the place above the burning layer, it's not changing, right? It's totally constant. Okay? So, and I can set everything at the surface to 0. So I get the really difficult calculation, which means I can even do it, right? Which is as I go into the star, the radiation pressure is just some constant times the total pressure. This P is the total pressure. Okay, everybody with me? That's great, right? So this is just then 1/3 a T to the 4th is L over L Eddington. Let's do the case where L over L Eddington is small. A small parameter, then this pressure is just the gas pressure. That's just rho kBT over mu MP. By the way, I'm doing ideal gas because I'm not degenerate. I'm just telling you, we're not degenerate. Degeneracy doesn't play almost any role in this calculation. And so now I'm done. I actually have a profile. So if you look at this equation, you can see that except for once I get rid of the constants, this just says that T cubed is proportional to rho. So as I go into the star, to higher densities, the temperature has to rise as T cubed. And now you can evaluate on the side, your question, which is this is convectively stable. Okay? Okay, so that's great. So I can now start to draw a plot, what that looks like over here. Rho is increasing as I go in. So I'm going to now... So now I'm going to plot log rho versus log T cubed. That's just a line. So as I go into the star, right, this relation is just T cubed proportional to rho, and it knows about L over L Eddington. So for a higher luminosity or higher accretion rate, I'd be on a higher profile. So as I increase m dot, I'd have a different profile as I go in. Okay? I'm not sure I answered your question.
You assume a thin layer in the beginning.
Geometrically thin.
Okay.
That's all.
There you assume that everything does not change.
No. No. Everything's changing. The luminosity is not changing. The mass is not changing. The radius is not changing. But I am moving slowly. So it's really...
Pressure gradient.
There's absolutely a pressure gradient. Yes. Yeah. I was going to. It's about to say. Just think the Earth. Yeah. Stroll, help me out there. The Earth's atmosphere. Yeah. Okay. So great. So the question is, this just keeps rising. Well, most of you know. Actually, I presume all of you know. That as I go up this curve, nuclear burning is eventually going to start to kick in. Right. Both the temperature and the density are rising. And so, how do we decide when that happens? Well, that's pretty simple. We just start to ask, when is the time scale for burning comparable to the time to get there? So let me just write this over here. So this profile survives until we reach high enough densities and temperatures, rho and T, to burn. Right? And that's when, of course, L will go down. Right? Because after I get through the burning region, luminosity is going to decline. Right? That was the plot I plotted at the beginning, which I've now erased. Okay? So any questions on that? And I'm going to derive the condition. Okay? Everybody good? Okay, so let me give you some time scales as I go into the star. As we go into the star, there's a few different time scales that are going to matter to us. One is what I'm going to call the accretion time. It's the mass above my head divided by m dot. So delta m is the mass coordinate above my location. So if I'm sitting here, it's how much mass is on top of me. And you can think of this as well as how long the fluid element has been on the star. And you can define the nuclear burning time scale, which is the energy release from the burning, the Q value, divided by epsilon rho T. So this is the time to deplete the fuel. Where epsilon rho and T is the nuclear energy generation rate. Okay, and that's of course in units of ergs per gram per second. So that depends on what we're burning, but that is a rate that depends on both the density and the temperature. Okay? And so if I were to make a schematic of these time scales on this, if I were to be so bold, let's try it. On this axis over here, I'm going to do something you used to be able to do. I'm going to write time scale. So as I go in, the time scale that I'm spending on the star is getting longer and longer, right? As I move into the star. So there's some curve. Sorry. Get myself some room. Okay, so there's some time scale for the accretion time, right? So if I'm going deeper into the star, it takes a longer time. But what about this nuclear burning time? Well, Q is just a number, but this epsilon is going to rise as I go in, right? As I go in, the density and temperature are rising. This reaction rate is going to dramatically increase, and so there's going to be some other curve, which I'm just making up, which is this T nuke. And so there's going to be a place, a location, where eventually these two cross, and this is going to be the region in which you burn. So basically, if you're a fluid element, you should think of it as you just suffer compression for some period of time until eventually the density and temperature get hot enough that you then undergo nuclear fusion, and then the further compression is now of the ash, which is basically helium in this case. Okay? So that's it. So we're done. We've done the problem. There is some detailed physics, which I'll just show you the results of. I don't want to do it at the blackboard because this is tedious. But this does tell us that the burning location is where these two timescales are comparable. And so I can go over here and just say that the burning occurs where delta M over m dot is of order Q over epsilon rho T. Right? And this is what I have to solve. Okay? And I'll show you the results of that. Obviously, this depends on what we're burning. I'm going to burn first hydrogen via the CNO cycle. Later on, we'll burn helium. But this is just the generic equation. And delta M, of course, relates to the pressure. So if I go back to hydrostatic balance, let me just remind you of that. I can also write the pressure in this coordinate, which is going to be gravity delta M over 4 pi r squared. So it's delta M gm over 4 pi r to the fourth. So the pressure rises as I go into mass coordinate, just as it does for an atmosphere. Okay. Okay, so this profile is going to go in. Eventually, it's going to start to burn. And now I have to ask, so I can build a stable solution. And before I show those results, I want to talk about the nature of the instability and how we check whether this solution is actually stable. Okay, that's what I want to do now. So any questions about how we find this supposed stable solution? Well, not supposed, it is true. It's a true stable solution. The way I derive it, but I have to check for stability. Yeah?
Does this intersection occur in the same region we were talking about?
Yes.
Necessarily?
No. For this case, it does. When we're doing some other cases, it may not necessarily be a thin region. That's correct. So it's not obvious that it would be. There's nothing I've shown you that says that it's obviously thin. You're right. I haven't proven that it's thin.
So that's how we determine the depth of the region.
So you have to check after the fact and see whether you've actually found a solution that's indeed geometrically thin.
Okay.
And typically it is, but there's definitely regimes where it's not always. That's right. Yep. Yep. Yes?
Going back, why does luminosity decrease when you start burning?
The reason for that is that the equation for if I'm actually undergoing fusion reactions or any kind of energy generation in the star, what's changing the mass, the luminosity per mass is just that epsilon. And so if I have a finite epsilon as I go in, I'm going to undergo a decline in the luminosity. Just think of it as basically I'm getting into the place where as I go deeper and deeper, I mean, that's the place where the luminosity is generated. So if you start from the inside and went out, you wouldn't be surprised. Zero luminosity, I had a big burning region. Now I have finite luminosity. It's finite forever. So it's just because I'm doing the problem backwards, because that's how I like to do it from the outside.
At the specific place does not decrease.
It does.
It does.
It does. The luminosity decreases. Yes. So the luminosity as a function of mass is as I drew it. So if this is going into the star, it's finite, and then it drops down. And this is the burning region.
In
Yeah.
space, not in time.
This is a time-independent solution. That's right. Yeah, time-independent. So just think.
There was no flux below the ground, and there was a big flux. There was a constant luminosity above.
Right. That's right. Okay. Okay. So that's my solution. So now all I want to do is ask, is it thermally stable? And so I have to check for a thermal instability. So let's do that. So the question we want to ask is my solution stable to a thermal perturbation. Okay? And so what I have to do is write down the entropy equation. So let me just write this out and then talk about it. So the entropy equation for a fluid element is given by energy generated within the fluid element and heat going in and out of the fluid element due to radiative diffusion. So typically you'd write it like this if you were doing sort of the fundamental, which is this 1 over rho del dot F. But for a star in 1D, we always write it as this dLdm. Okay? So what I've done so far is I've assumed steady state. So I've assumed that epsilon nuc is dLdm. Now I'm going to relax that. I'm going to take a solution that is indeed satisfying this, but I'm going to perturb it. And I'm going to see on the left-hand side whether this temperature is going to decline or not, or grow. Right? So if I just have heat transfer and I go in and I put in a thermal perturbation, the thermal perturbation is just going to wash out. But if I have nuclear reactions, maybe when I do a thermal perturbation, the nuclear reactions take off and win. Right? And that's going to be the race. And so I'm going to assume for now, and you can read the texts about why this can be risky, I'm going to do a constant pressure perturbation. In the thin limit, that's a pretty good assumption. And so the left-hand side then just becomes Cp dt dt. This is epsilon nuc still. And I'm going to keep this right now as 1 over rho. Okay? So I'd have to perturb two quantities. It's really a race. Will the thermal diffusion win or will the nuclear energy win? Right? That's the race. Is there a question? Everybody good? Okay. So now this is where it gets really dangerous at the blackboard, because I have to make a fair amount of assumptions to keep it at the blackboard. In reality, of course, I have a profile, I have multiple locations, I don't have one pressure, I have a range where the burning's occurring, I don't have one temperature. But of course, I want to do something to keep it tractable. And so let me start by writing down this term. This is, if you want to think of it in a one-zone model, which is what I'm going to do. And then, of course, we'll show you the real answer. I wouldn't be doing this if it didn't work. Okay? It works reasonably well, so it's worth showing. Okay? So let's first start with this. I'm going to call this thing epsilon cool, this guy. So that's 1 over rho. And then it's going to be a gradient of the flux, which is again C over kappa rho ddr of, I'm going to leave it as 1/3 AT to the 4th. Okay, so that's that term. I haven't done anything yet. I'm just writing it out. And I have hydrostatic balance, which is that dp dr is minus rho g. And so that means that dp over g is minus rho dr. Okay, I'm going to do that because it's helpful. So you may notice I've got 2 rho drs here. Okay, so I'm going to first just put in for all of that the dp's. So if I can do that without screwing it up, let's see. This is where jet lag will get me. I'm going to get a sign wrong, but somebody will fix it for me. C over kappa ddp of 1/3 a g to the 4th. I probably lost a sign or two. Let's not worry about it. I think I'm still good. Yep. Okay. So this is C and kappa are constant, right? A is a constant. And so the one zone model just says that wherever this burning is occurring in the burning layer, this dP is just a fixed quantity. And so all you're really going to worry about for this cooling rate is basically the temperature perturbation here. So just think of it as it's a fixed column of material. That's the fixed dP. And as I go in and I increase the temperature, right, if I have a thick region that's yay thick, you've done this, you cook probably. Right, if I go in and I increase the temperature in the middle, you can calculate how much more the flux is going to come out. And that's pretty much what this term is. So this one is proportional in the end. This is going to be proportional to just t to the fourth. Everything else we're just going to assume is constant when we do the perturbation. Okay? So this is the one zone model. This is the beauty or ugliness of the one zone model. Okay. Which? Opacity?
No, constant density in order to assume.
No, I got rid of density. So by using hydrostatic balance, I got rid of density, which I wanted to do. Because we're going to see the density can change a lot. So as I increase the temperature, if I'm doing a constant pressure perturbation, I've increased the temperature, the density will decline. But the amount of stuff on your head doesn't decline, right? So pressure is a better coordinate just because it isn't changing that much, whereas other variables can change. The point is the time it takes to build the envelope, which is basically what sets the pressure, is much, much, much longer than all these time scales, is what we're going to find. There's a hierarchy of time scales that I haven't fully taken advantage of yet. Okay, so that's one term. That's going to be this term, right? But what I have to now calculate is what's the perturbation. So what that means is I'm going to presume that epsilon cool is just proportional to t to the fourth. Okay, we're almost there. All right, block my eraser. No? Yeah. Okay. Okay. The last term I have to get before I do the perturbation is how will the epsilon change? So again, this is my nuclear burning rate. It depends on both the density and the temperature. Of course, you know it depends much more sensitively on the temperature than the density, but the density dependence is all important, as I'm going to show you. It's a little bit surprising. So let's do this simply first. So let's just imagine I'm going to perturb this quantity. So I'm just going to define some variables. So I'm going to have two things, which is d log epsilon d log t, delta t over t, plus a d log epsilon d log rho, delta rho over rho, where these deltas are my perturbed quantities. Okay? So this is just saying how will the rate change as I change the temperature or as I change the density. And so these are just properties of the nuclear burning. This will be the temperature sensitivity of the reaction rate. This will be the density sensitivity of the reaction. Okay? So this is a very high power. This number is going to be a very high power, maybe of order 10 for the CNO cycle. This one is actually linear for the CNO cycle. It's just 1. This number is 1. Okay? So that's just, let's keep that in mind. So roughly nu is going to be this one, d log epsilon d log t. And it's about 10 for CNO burning at the relevant temperature for stable burning, which is, it's going to sound really high to those of you who've done this problem. It's about 10 to the 8 Kelvin when you're doing stable burning. It's extremely hot. So this number is about 10, and this number is just about 1. Okay. So what we want to do is do a perturbation of this equation. So let's write this equation and keep it over here. Epsilon nuc, I'm going to call this epsilon cool. Okay. So I'm going to hold this equation, but this is what we're going to be perturbing in a moment. But what I need, I'm almost there. I still need to do one more thing on this side, so I just want to keep that equation. Okay, let me pause and see if there's a question. Then I've just got one more line of algebra, which is only 5 lines, but I'll exaggerate. Yeah. Good.
Before we are talking about we have stiffening, constant luminosity, and we have energy injection only at the inner boundary. And right now we are talking about the perturbation and just at the inner boundary. Is it stable?
Yeah. So there's a region of finite thickness, but thin relative to the radius of the star. So let's do it here. The core. I'm in this room, right? If I say the burning layer is in this room, it's yay thick. That thickness is, I can measure it, its extent, but it's still very small compared to the distance of the core. So that's my delta, either the burning layer or the advection layer, it doesn't really matter. But it's still geometrically thin, which means that the pressure is nearly constant during any perturbation, because I can't change the amount of stuff on my head.
So when we talk about perturbation, we just mean the perturbation at the inner boundary.
I'm going to do a perturbation just in the burning layer. That's right. Right. But don't think of it as a boundary condition. Think of it as a finite region. It has a finite thickness. It has to have a finite thickness because I'm going to perturb it somewhere and heat's going to go out either side. So you should think of it as it is a finite thickness. It has to be. Because heat's going to go either way. I'm just going to worry about it going up. Yeah.
So, that do you need to assume the gas pressure dominant in this hydroequilibrium state? Because
No. I don't need to assume that. You finish your thought.
Because I saw you write down this hydroequilibrium equation, things only the pressure is only gas pressure kicking to support the layer.
So,
minus equal to minus rho g, and then I saw.
so that's the total pressure in that equation, and the radiation pressure can be very important. So as we go to the Eddington limit, remember my trivial equation was that P rad is L over L Eddington times total pressure. So as the luminosity approaches the Eddington limit, we'll find that the total pressure, the radiation pressure is becoming comparable to the total pressure. So we will get into the regime where the radiation pressure is important, for sure. Yep. Yep. And that's going to be crucial to the stabilization, actually. All right. And actually, we can do that right now. Okay, so here we go. You asked it, you're going to get it. So my total pressure is that. All right? There's two terms, the gas pressure and a radiation pressure. And I'm going to do a perturbation where the pressure is not perturbed. And that's going to give me a relation from the equation of state between the temperature perturbation and the density perturbation. So if I take this equation and I perturb it with a constant pressure, I get a relationship between the density and the temperature that looks like this. I'm skipping steps, but that's what that equation looks like. Okay, so if the radiation pressure is 0, then delta rho and delta T are anticorrelated, as you'd expect for constant pressure. But what we're going to find is if the radiation pressure is becoming important, I get an even larger density decline for a given temperature contrast. Okay, right? So that's just this equation perturbed. Right, and I'm not going to use beta. I hate beta. For those of you who use beta, I highly recommend against it. Because every time I use beta, I get confused. P rad over P gas. I'm not going to dimensionalize it. Okay? So that's a simple perturbation equation. So this is important. Why? This is important because we're going to find as the radiation pressure gets important, and I have a temperature perturbation in this region, the density decline is going to shut off the burning. Okay? And so this is the thing that is why nuclear burning can be stabilized in the white dwarf case. Okay. So now let me just go back to this equation. Right, so let me just write this out. So this is going to be epsilon nuc. I'm just going to call this, let's write this as epsilon, let's write it this way, minus epsilon naught t over some t naught to the fourth. So t naught is my fiducial temperature that I found, right? And epsilon naught is the rate, right? So for my steady state solution, there is a temperature I found, and there's a value for these two numbers. Of course, they're exactly canceling in steady state, right? And so if I just do a perturbation of this equation, then I'm going to do this as ddt of a t naught plus delta t. All right, and this term, the t naught is 0, so this is just trivially dt of delta t. All right, so that's the left-hand side, sorry. All right, so the left-hand side of the equation is going to just tell me whether the temperature declines or not. Heat capacity is positive for this case. For a normal star, it's negative. This is an unusual thing about thin shells. So Cp is positive. So what all we have to ask is the right-hand side growing or not under the perturbation? Okay. Okay, does everybody see where I'm going? So all I have to do now, so this perturbation is trivial. This just goes t to t naught, t goes to t naught plus delta t. So this just gives me a simple term that looks like 4 in the logarithmic derivative, and this is the one I have to do now. Okay, so let's write this all out. So the right-hand side looks like then epsilon naught delta t over t naught times nu minus 1 minus 4 p rad over p gas minus 4 epsilon naught delta t over t naught. Right? So this term is the cooling term, and this term is the nuclear reaction term. So this nu is the d log epsilon d log t, and then this is 1 this is the d log epsilon d log rho, and that's the correction factor, which I've just derived here. So that's the right-hand side. So if I weren't doing this carefully, it would be the trivial thing. If I just wrote this as t over t naught to nu, it just nu's bigger than 4, you're done. Does everybody see that? Right? I mean, this is just, it's going like t to the 4th, this is going like t to the 10th, you win. Okay? It's more subtle because of this term. Right? And this is the term that really matters, as I'm going to show you, for the white dwarfs. Okay? So if I want to have an unstable case, I just then want this right-hand side to be positive, and that just means that nu has got to be bigger than 1 plus 4, 1 plus p rad over p gas. Unstable. That's it. If I did it right. Yep. Okay. So nu is 10 for CNO burning. Right? And so you can solve this equation for what p rad over p gas had better be, and you can see if p rad over p gas is small, right, then it's always unstable, because 10 is bigger than 5. Okay? But as I get near the Eddington limit, and p rad over p gas increases, I can stabilize the burning. And you're stabilizing the burning simply because during a perturbation, zero pressure perturbation, the density decline when you're radiation dominated shuts off the nuclear burning. Okay? And so this gives you, if you just do that algebra for this value, that would say that I stabilize burning when L over L Eddington is greater than about 1/5. Okay? That's it. I'm stable. Okay. And that ends the blackboard. Questions? So what we're going to find is the nuclear burning is always unstable unless I'm accreting at a rate very close to what I need to get to the Eddington limit. And so there's going to just be a narrow band of stable accretion. Otherwise, it's always going to be unstable. Okay? By unstable, I mean that if I build a steady state burning solution and I do a thermal perturbation, it runs away, which means I've got the wrong answer, which means I haven't actually solved the problem. Okay, which I have to tell you is what happens in that case. Right? So remember, the hypothesis is I'm going to burn it at the rate I accumulate. What I've shown is that there's only a narrow regime above about 150 Eddington where I can build a model that is steadily burning and it stays steadily burning. All the other models are thermally unstable. And there's not a solution, there's not a steady state solution. Udi?
Can you go above there? You cannot go above there.
No.
No
No.
room here.
Right, exactly, correct. Yeah, correct. Not much room. Exactly. That's right. Not much room.
Can you start with an unstable solution in which the luminosity will increase, will turn and this will turn to the stable regime?
Well, in this case, the only luminosity I have is that from burning. If I have luminosity from underneath, somehow, I can start to modify the story. In this case, I'm assuming the L is tied to the accretion. But if I have a hot bottom boundary, I can stabilize burning that way too. I don't think that's really your question, though.
No, I forgot that the L is tied to the luminosity.
Yeah, so in this case, the luminosity is tied to the accretion rate. Okay, yeah.
What process, so like what story can we tell process about
Say again?
L? What story can we say about L being equal to L Eddington? What's the situation?
So for the case I'm talking about, remember the luminosity of the star is determined by nuclear burning of the matter I'm accreting. So I'm saying L is Q times m dot, right? And so this translates into an accretion rate. This means the accretion rate has to be only 20% of the Eddington rate or up to 100% to be stably burning. Otherwise, it's all unstable.
Just in the sense of luminosity, like what? If a star has L equal to L Eddington, for the stability discussion,
Yeah.
what can we say about it? I mean, about the radiation or something like that?
Well, yeah, if you're getting near the Eddington, I mean, this is just the, as you get near the Eddington limit, right, the radiation pressure becomes more and more important, as I showed sort of at the very beginning, right? And so, I mean, there's a lot of things that happen at or near the Eddington limit, especially if you're constant opacity. So, you know, in reality, stars aren't constant opacity. So, I mean, I'm assuming there's only one opacity in this problem. So when you get near the Eddington limit, you have to start worrying about where's the opacity really the biggest value. And there's a whole industry about that, which I'm, you know, you could give lectures on that, whole lectures. Well, you could give a whole series of lectures on what happens at or near the Eddington limit, which I'm not going to do. So,
Generally say that you're not accreting anymore.
if you try to supply so much fuel onto it that exceeds the Eddington limit, the expectation is that it'll burn the maximum it can, and the rest of that material will not join the star. Typically, the argument is it becomes a red giant. But if you're in a binary, you might not have room to make a red giant. So, okay. Any more questions on this? I think I'm ready to go back. I'm ready to go back. We have to wait. There he goes. Okay. Yep.
Things change if you include Marley ever on the page.
For the temperatures I'm at, it's all CNO burning. Yeah, the PP chain doesn't matter. The fast rate is CNO. Yeah.
Okay, so you
Yeah.
could have, I don't know, lower temperatures, could you have situations where PP would be important?
For the stable case, it's always CNO. yeah, you can't have PP burning for the stable. For the unstable cases I'm going to talk about, PP burning does start to matter. But for the stable cases, you're always so hot that it's CNO. Yeah. Okay. So just to show you first where you land in rho T space. So this is just sort of the onezone model calculation that Ken Chen did for his thesis a decade ago. It's a little bit shocking to me. Time is flying. Probably more shocking to Ken that it's been a decade than to me. But so what's shown here are at solar metallicity. So this is in rho T space. So here's the density of the fluid element, the temperature of the fluid element. So these open circles are the unstable solutions. These are all for different accretion rates, but you can see the typical temperature and density. This is what I didn't want to solve, but we're typically at 10 to 100 grams. We're typically at temperatures of around 10 to the 8. The stable solutions are over here. Here's the beta. I hate beta, but Ken loves it. Beta of 1/2, so that's roughly equal gas pressure and equal, wait, see, I can't remember what beta is. Help me out. Does anybody remember? Which ratio is it? See, that's why it's useless. That's why it's useless. Okay, the point is this is on this side you're more radiation pressure dominated, okay? These are for a 0.5 solar mass and for a 1.35, okay? Just to set the stage, here's helium burning. You can do the same calculation. These are all the unstable cases and the stable cases. What about accretion? What about so this is again from Ken's paper. This is just the onezone model. Okay, so this is literally the analytics I just showed you, a little bit gussied up. The stable burning regime is this narrow regime. Note the number of around. I was saying it was a few by. It's gone. It's long gone. Eddington rate I think was 4 × 10⁻⁷. I said for a 1, so that's about right. There's the Eddington limit, and here's the roughly the 1/5. Okay, so there's the narrow regime. Here's a great plot from Eben and Tudikov, which shows this, again, as a function of mass of the core, mass of the white dwarf, for hydrogen helium accretion. So this is the stable hydrogen burning regime. And then remember I said for helium, because the Q value is different, the opacity is different, it's about a factor of almost 10 higher. So here it is. Here's the stable helium burning accretion rates, which are much higher. Okay, so as we start to do, I'm going to now focus on this case for the rest of the talk today. And I'm going to tomorrow start talking about this other case for the helium burning. But you can see the issue, if you're on a star and you're doing stable hydrogen burning, building up a helium shell, the helium shell you've accumulated is always unstable because it's below this rate. Right? This is a big issue for using hydrogen to make type 1As, which is why basically, in my view, it just doesn't work because the helium burning is always unstable. Okay. So for the remainder, I'm going to just stay to this and launch into showing some results. Of course, all the results I'm going to show you from our group are using MESA. I always have to show the photo of Bill Paxton. If you've never met Bill, he's a little bit time invariant. He works the same all the time. The amount of users are growing for MESA. Of course, all of you are using MESA. If you're not, you can come to summer school next summer. We do this every August in Santa Barbara. So the next one is August 13 to 17. We'll announce it at the AAS meeting. And every 2 years, we have this beautiful experience of writing an instrument paper. So Evan and Jared are in the room. They're the ones who are laughing, Evan and Jared. Josiah Schwab was the leader this time. So for those of you who don't know this, it's important. The MESA instrument papers are the papers you need to read that tell you what we believe you can use MESA for safely. If you're outside the bounds of what's in an instrument paper, that's your choice. But we do our best about every 2 years to try to summarize the capabilities in the code where we've been able to compare to others and do things. And so that is this instrument paper. And they're always, the first author is always Bill. And now the standard is the second author is the person that did all of the hard work, heavy lifting, and wrangling of the other 13 authors. And that was Josiah Schwab this cycle. So when you see Josiah, congratulate him. And of course, Mesa's, here's the Frank Timmies loves to make this plot of where the MESA users are. Every time I show this plot, some person in Hawaii complains because there's not a place in Hawaii. But Israel's definitely here. Yeah. So what happens if you run MESA and just now not do a one-zone problem, but do the real problem, right? So this is what you get for hydrogen burning. So here's the stable regime that you get. It's maybe 30% different than the one-zone model. This is found by actually running the code and finding that the model is stable because you run the code and it doesn't change in time. Or it starts to undergo flashes. So what happens when you're unstable is you have period of accumulation, a flash, and a period of accumulation. So it enters a limit cycle. What's shown here on this plot is the time scale of the limit cycle. So along this line, for that accretion rate and that mass, the recurrence time of the flash would be 3,000 years, all the way up to here to 1 year. Okay? So just as you become beneath the stable line, you go unstable, and unstable means a limit cycle. And the violence of that limit cycle can really vary. But this gives you a sense for the typical durations at these high accretion rates. As we're going to see for classical novae, their accretion rates are down by 1 to 2 orders of magnitude. And so the recurrence times are going to be extremely long, 10,000 years or something. If you see it twice, if you see a novae twice, it then becomes a recurrent novae, which means you've seen it twice. The physics is identical. If it's a recurrent novae and you've seen it twice, it probably means it has to sit with a recurrence time less than 300 years, let's say, or maybe less than 100 years, depending, or if it's a graduate student. Okay. But so the point is, when you see a recurrent novae, it's in this regime. It's typically a higher mass and a higher accretion rate, right? You can just read it off the plot. Okay. What does unstable burning look like? Well, so here's a point that is a 1 solar mass accreting at around 10 to the minus 7. So it's just beneath the stability curve, and this is what it looks like if you run MESA. This is the luminosity coming out of the white dwarf, so it's undergoing cycles. You can see the dynamic range is about a factor of 100. This shows the amount of hydrogen that builds up, burns, builds up, and burns. Recurrence time, you can see, is about 50 years. It's pretty much what's on this plot. Sort of sitting, I kind of put it where I should have put it. But this gives you a sense of the recurrent cycle. So what does it look like over time? Well, it's very different than the solution I showed you. Because you have this long period of accumulation where the luminosity coming through the star is not Q times m dot at all. It's a much lower luminosity because there's almost no nuclear burning happening. And so the value of the temperature, so you can see it here. This is not coming out well. Here's P radic as P gas. I'm happy to say we don't use beta. But you can see you're and this is a case that's actually, this is a low accretion rate, 10 to the minus 9. But again, you're in an accumulating phase. So this is density on this axis, temperature on that axis. You're in an accumulating phase. Eventually, the base of the accumulated layer gets to a temperature hot enough that the hydrogen burning takes off. It's so unstable, it does trigger convection. So here's a convection zone that's actively convecting. This is where the runaway is occurring. You can see the density is around 1,000, so it's denser than what it would have been. It accumulated more, and the temperature is running away, and it just keeps running away. There's nothing that's going to stop this, basically. And so it gets all the way up to the Eddington luminosity, at which point it's now burning the fuel as fast as it possibly can and trying to get the heat out. So it's really it's a real thermonuclear instability. If you're watching from the outside, what you see would be this in the HR diagram, which is the rise. So this is a constant radius line in the HR diagram. So the star is still compact, but heat's coming out. As you approach the Eddington limit, of course, the envelope expands dramatically and comes somewhere way over here. This is the most challenging part for all of us today, which is how to understand the expansion of the envelope when you're at or near the Eddington limit, especially in a tight binary. So you can do an isolated calculation, but in reality, you're in a binary, and the first thing that happens is the white dwarf radius exceeds the Roche lobe. And so you have something happening. And that is, I would say, pretty much our biggest problem right now, that we don't really have a good solution to. So I'm not going to show you too much data of what novae look like, because they're a mess. But I thought this was a really nice recent result that I just want to highlight, because it also shows some of our ignorance. So this is a nearby novae in our galaxy. So first off, this is the I magnitude on this scale. So this gives you a sense of how dramatic these things are. So it's sitting down here at 19th magnitude. At peak, it gets almost naked eye, around 7th. So you can see the contrast for this one in brightness is a factor of, well, what, 12 magnitudes, roughly. So an extreme contrast. This is a funny time plot. Time 0, because they have days past 1st of June 2012. So these are minus days this way, positive. So they've got just a few days here of the rise in optical. And then this region in the gray is where they saw this with gamma rays. So one of the really interesting new puzzles about novae is that for almost all of them in our galaxy where you can look at them and see them, you see gamma ray emission during the Novae event. Very high energy gamma ray emission. This most likely has to do with this ejection puzzle, which is how does the mass escape, and the likelihood that there's internal shocks because the mass is leaving maybe by super Eddington winds, maybe by Roche lobe overflow, maybe by both. The typical velocities that we observe are thousands of kilometers per second for the ejected, but there's a lot of diversity in the velocity. And there's not a simple explanation for that. Maybe there's also some common envelope-like activity that sort of Stroll was talking about today. And so this is sort of, to me, one of the sort of real frontiers of the problem, which is the gamma ray emission is really telling us that there are internal shocks and a large variety of different types of velocities. And I'm not going to get into this in this lecture because it's pretty uncertain stuff. So let me pause there and then I'll launch into the next thing. And who's watching the clock? Huh?
Yeah, I think that's...
This is where I stop?
Yeah.
This is where I stop. Oh, it's even better. Good.
Okay, so let's thank Lars.
Okay.